Hey, wait, North, Mr. Yurgler here. Let's talk about rate laws. We're going to start on writing the rate expression for a reaction, and then we can talk about how we can use that to calculate concentrations, times, rates, and other stuff regarding the kinetics of a reaction. All right, there's three different types. Average. We can also do instantaneous, which is a little more tricky, and then relative rates as well. Let's talk about average rates first. So if we look at this reaction as an example, this table is giving us the concentration of our chlorobutane, which is this reactant here, over time, right? So we start at 0.1 molar, that's moles per liter, and every 50 seconds we're taking a measurement and the concentration is decreasing over time because the reaction is proceeding. Now, in all of these 50-second intervals, we can calculate an average rate, and the average rate is going to be the change in concentration over the time for that time interval, right? So in this example, our time interval is 50 seconds. We're taking a measurement of the concentration every 50 seconds, and so our change in time is 50 seconds, and then we would want to look at the change in concentration over that time period. Okay, so this right here, take a look at where this is coming from. 0.1 is our initial, so at time 0, and then 50 seconds later, our concentration is 0.0905. So that is where they're getting the 1.9 times 10 to the negative fourth. So this is our average rate for that 50-second interval. Notice that the average rate is decreasing over time, right? The reaction is the fastest at the very beginning because our concentrations are the highest. As we lose our concentration of our reactants over time, the rate decreases more and more because we have fewer and fewer collisions that can happen with the right orientation and energy to create more product. Let's look at another example. Take a look at this data. So here we have two different time intervals, our initial and then two time intervals after that initial, those initial conditions. A lot of times the initial conditions are going to be 100% reactant. Calculate the change in concentration, your average rate, over the first 50 seconds. Go ahead and pause the video and do that right now. All right, you should have done something like this, where we look at our change in concentration over our change in time. And it tells us to do the first 50 seconds. We could have done from 50 to 100 as well. But in this case, it's final minus initial. It's always going to be final minus initial, and over our 50 seconds. Notice that it comes out negative. And that will always be the case if we're doing final minus initial. If our concentration is decreasing, it will always be negative. If you know that you have a reactant and it should be decreasing and your number doesn't come out negative, then you can actually go ahead, I would go back and double check your numbers, but we should just go ahead and make all reactants negative and all products positive, because products are always increasing, reactants are always decreasing. Now let's look at instantaneous reaction rates. Again, a rate is a change in concentration over a specific time interval, and with the average reaction rate, we're looking at a relatively large time interval. With instantaneous reaction rates, we're basically looking at a split second. What is the reaction rate in that split second? We would need to collect a lot of good data on this in order to do it. And what you have to do is basically find the slope or the derivative at a certain point, right? So just looking at this, we can tell right away we have one reactant because one is decreasing, and NO and O2 are our two products, okay? Reactants are always decreasing, products are always increasing. The instantaneous rate at a given time point would be the slope of that line, the rise over run at that particular point. All right, now relative rates. This can get a little confusing. This is where we compare the rate of one reactant to the rate of another reactant or product. And so that's why it's called relative, because they're relative to each other. We're going to focus on the disappearance of reactants or the appearance of products, okay, or one of each. I've mentioned this already, and here it is again. It's a big point. The rate of change, delta is always change, of a reactant is always negative. The rate of change of a product is always positive. Here's our example. So H2 and I2 produce HI. Now, looking at the stoichiometric relationship here, we have a mole ratio of 1 to 1 to 2, right? It would be the case that HI is forming at twice the rate, or in half the time. That'd be the same thing as saying half the time, as H2 disappears. Picture the molecules. We have one molecule of H2, and for every one molecule of H2 that we lose, that we react with I2, we're producing twice as many molecules of HI, right? And so we're producing HI at twice the rate of the disappearance of H2. Now this is where it gets a little tricky. What we typically do is we take that coefficient and we put 1 over the coefficient. I'll show you that in the next slide. Think about this logically. The rate of the decrease of H2 is half the rate of the increase of HI, right? Because HI is increasing at twice the rate. I'm not saying that for every H2 that we make or that we use up, we're producing half as much HI. That's not true. Emphasis is on the word rate, right? And that it's over time. It's a change in concentration over time. So the rate of H2 is equal to half the rate of HI. And that makes sense when we look at our stoichiometric balanced equation. Here's a more generic format. So in any reaction, we take the coefficient and put 1 over the coefficient. Okay, so 1 over A for the concentration of A changing, and so on. A couple things to note. Notice the reactants are always negative, right? There's the third time that's come up. And let's go back to this example again. The coefficient on the H2 is 1, and so it's essentially 1 over 1, or just negative 1. And the coefficient on HI is 2, and so it's 1 over 2, right? And again, this is saying that the rate of one is equal to half the rate of the other. Or imagine B is 3, right, in your balanced equation. The rate of the change of A, if A is 1, would it be equal to a third of the rate of the change of B, meaning that B is being produced or being used. In this case, it's a reactant, so it's being used 3 times as fast, right? Which means that the rate of A is equal to a third of the rate of B. Let's look at another example to kind of wrap our heads around this a little bit. Looking at this equation, think about this logically. Oxygen can only appear half as quickly as the nitrogen dioxide disappears, right? We're going to use up 2 of these in order to make 1 of these. It is also true that NO appears twice as fast as oxygen appears, right? We're creating product, but we're going to be creating NO at twice the rate of oxygen. And so here's the rate of our reaction. Notice that the reactant is negative, and it's 1 over 2 because our coefficient is 2. 1 equals 1 over 2 for this product, and 1 over 1 for this one, right? Now, it might be a little bit easier. It might make more sense. You'll see these fractions a lot, but it might make more sense for you to take them all times 2 in this case to cancel out the fractions. And you can think of it in terms of the relative rates are -1 to +1 to 2. We can think about this logically and kind of reason our way through it, but I also encourage you just to go with the pattern of putting 1 over the coefficient, and you'll never go wrong. All right, this is Mr. Yergor signing out.